This section is bridging enterprise networks with serial WAN technology as a means of building connectivity between the enterprise and external networks. Serial has in recent years been slowly phased out in many parts of all networks in favor of Ethernet technology, however still remains active as a legacy technology in a great number of enterprise networks alongside Ethernet. Serial has traditionally provided solutions for communication over long distances, and therefore remains a prominent technology for wide area network or WAN communication, for which many protocols and legacy WAN technologies remain in operation at the enterprise edge. A thorough knowledge of these technologies is required to support many aspects of WAN operation. So upon completion of this section, it is generally expected that trainees will be able to explain how data is carried over a serial-based medium, as well as configure link layer protocols for serial links. Serial-based communication differs greatly from the Ethernet networks that we have primarily focused on, and while much of the scope of IP networks will be focused on Ethernet-based networks, there is likely to be some networks that still depend on serial-based media. We focus here on introducing the general principles surrounding serial transmissions and the application of serial technology in supporting more legacy forms of communication that may exist as part of wide area network solutions that may be adopted for branch office and other forms of remote network communications. As with all forms of physical communication, signaling over serial is subject to requirements for synchronization of signals between the link layer sender and receiver, as well as being subject to rules for processing of such signals by the receiver. There are in fact two forms of signal synchronization that may be applied over serial links. The first of these is asynchronous signaling and involves the addition of bits to the transmitted data. These bits are known as start and stop bits that allow the receiving interface to be aware of the incoming frame and as such maintain synchronization of the frame rate. These additional bits, however, take up a large ratio of the overall frame, resulting in high overhead. The other form is known as synchronous signaling and is based on a clocking mechanism that is managed by one of the peering devices. This device is referred to as the Data Circuit Terminating Equipment, or DCE, and is basically the device that synchronizes the clocking between the sender and receiver, with the clocking information included as part of the data signal. The peering device is understood to be the Data Terminal Equipment, or DTE. With regards to Ethernet technologies, we have looked at the Ethernet frame and how it is used to support data link communication, relying greatly on MAC addressing for referencing the source and destination within a multi-access network that may often support multiple end stations. With serial, however, a separate set of data link-based protocols are needed, and these protocols mainly operate in a manner to support point-to-point communication over a serial medium. The high-level data link protocol, or HDLC as it's commonly known, is one of two serial-based protocols that are used to support link layer-based data forwarding. HDLC is capable of supporting both synchronous and asynchronous-based signaling, and we show here the general format of the HDLC frame. The frame itself consists of flag fields that mark the start and end of the frame, along with an address field that is, for the most part, unused, however allows HDLC to support multi-point type networks involving multiple terminals. However, we focus here on the more common point-to-point application of HDLC. There are three standards of frame type that exist, including information, supervisory, and unnumbered, and these are identified through a control field. However, with Huawei products, only the information frame type represented by I here is used. The frame check sequence, like with Ethernet, is used to ensure the integrity of the frame is maintained, meaning errors in the frame can be detected. The information field contains the fields relative to the frame type used. For information frame types, this includes the NS, send, and NR receive sequence numbers, along with pole and final bits for communicating status information. The establishment of HDLC as the link layer protocol for serial requires very little configuration. It is important, however, to remember that the same protocol should be configured for both interfaces connected in a point-to-point fashion over the same serial medium. Looking at the example configuration, we can see that the serial interface view has been entered for interface serial 1/0/0, under which the link protocol HDLC command is used to establish the protocol at layer 2. A prompt in VRP will be given to confirm the changes, following which HDLC frames will be used. The assigning of IP unnumbered addresses is a feature that is able to support serial point-to-point networks without requiring that a unique IP address be assigned to the interface, and may commonly be applied where services such as DSL and dial-up connections are supported to conserve IP addresses. The interface is able to borrow the address from another interface, such as the loopback interface as we demonstrate in this example. In order to achieve this, we simply specify the active interface to which an IP address is assigned that is to be borrowed by the point-to-point associated serial interface using the IP address unnumbered command under the serial interface view. Once the IP unnumbered configuration has been implemented, we are able to use the display IP interface brief command to view a summary of the IP assignments for the device interfaces. As we can see from this example, the loopback interface address of 10.1.1.1/32 has now been borrowed and assigned to the interface of serial 1/0/0. Another link layer protocol supported for serial networks is the point-to-point protocol, or PPP, that is again capable of supporting both synchronous and asynchronous links. The PPP protocol is able to support multiple network layer protocols, as well as having supporting features for authentication, as well as self-configuration of addressing through the IPCP, or Internet Protocol Control Protocol. And we shall take a look at these features in more detail as we move on. There are three main components that make up the PPP protocol in the form of the encapsulation method, link control protocol, and network control protocol. As we have mentioned, PPP is capable of supporting different network layer protocols simultaneously over the same link. This is possible as a result of including frame instructions into the HDLC-like framing that is used by PPP, as we shall see shortly. As such, PPP is able to retain compatibility with a variety of upper layer protocols to support their encapsulation. The Link Control Protocol, or LCP, enables automatic agreement on encapsulation configuration options, detecting issues particularly with loopback links, authentication, and also supports the eventual termination of the link. The third main component is the Network Control Protocol, or NCP, that handles other issues such as IP address management through protocols such as IPCP. Establishing PPP links involves traversing a number of phases that not only supports the configuration and maintenance of the PPP link, but also its eventual termination. This process begins with the dead phase, which indicates that a link is not currently physically active. As soon as the link is detected as up, a transition to the link establishment phase will occur that relies on the link control protocol establishing connection through the negotiation of configuration options using configure packets. If authentication has been configured for the link, this will be performed to allow a peer to authenticate itself so that the network layer protocol packets can be exchanged. Since the authentication is optional, it may be bypassed and negotiation of network layer protocols be configured as part of the network phase. This step relies on NCP for support of a particular protocol, which most commonly will be for either IP or the newer IPv6 protocol. Termination may occur for reasons such as link failure, an idle connection timeout, failure to authenticate, or administrative intervention. Typically, however, terminate packets will be sent to tell the network protocols of the termination process. PPP will then signal to the physical layer to initiate termination of the link, after which the link dead phase is again established. We find that the general PPP frame has a very similar structure to that of HDLC, containing flag fields, address, control, protocol, and information fields. However, the application of these fields is used somewhat differently. The address field uses a single address to represent all stations within PPP, which kind of acts like a broadcast that serves little purpose for point-to-point links. The control field is fixed in PPP with a hexadecimal value of 03 that renders the field somewhat dormant. The protocol field, however, is responsible in PPP for identifying the upper layer protocols, which is particularly important since PPP is capable of supporting multiple network layer protocols over the same link. And so the protocol field must distinguish these different protocols. It will also be used to identify the packets of the different NCPs, such as IPCP, and even LCP associated protocols, such as those used for authentication. We demonstrate here an example of the type of packet that is carried as part of the information field header. In this instance, we use the LCP packet, since it is a central component of PPP, and is identified in the protocol header by the hexadecimal value of C021. For the actual LCP packet contained in the information field of the PPP HDLC-like frame, A code field exists that represents the different packet types used by LCP, with examples including configure request and terminate request types that are used for establishing and terminating the PPP connection. The identifier field helps to match requests and subsequent replies, while the length field indicates the length of the LCP packet. The data relates to the packet type listed in the code field, which may include parameters such as MIU and authentication that we shall look at very shortly. We will firstly take a closer look at the typical packet types that are generally referenced in the code field of the LCP packet. We list the first 4 packet types supported within the LCP packet here. That includes a configure request packet for requesting link establishment, configure ACK for approving the sent request, configure NACK for rejecting the request based on certain parameters in the data being recognized but not being accepted, and configure reject, which is when the parameters are not recognized. These packet types will also include types for supporting PPP termination and maintenance, such as echo packets for supporting performance testing and debugging. We reference here some of the typical parameters that have been mentioned, including the maximum receive unit or MRU, authentication protocol, and magic number. Certain packet types may carry these parameters depending on the operation and whether such features as authentication have been configured. The MRU lists the size of packets that a peer can receive and is sent to the peer to control the size of such received packets, which by default is 1500 bytes. The length listed in the length field of the LCP packet to be sent to a peer should not exceed the specified MRU set by that peer. If authentication is set, the authentication protocol parameter may be included in the LCP packet type, usually as part of a configure request, but only if authentication is to be performed. The magic number is another parameter that may be included, particularly to detect whether a loop exists. Very simply, the sender will generate a number, typically at random, that will be used as the magic number. If the number in the received configure request contains the same magic number as the last sent configure request packet, it is assumed that the same packet has also been received as a result of the link being looped back. There is also the small chance, however, that the sent and received magic number from a peer is the same, and so a configure NACK containing the magic number would be sent to better determine whether the link was really looped. We begin now to take a look at the typical operation involved to establish the PPP connection using the LCP packet and associated packet types and parameters. We start here with the 2 peering devices connected via a serial medium and assigned with IP addresses that will be used to support network layer communication. In support of the link negotiation process, we see that an LCP packet containing the configure request packet type is generated. This will typically contain parameters as we have introduced, such as the MIU and any authentication that is later to be negotiated within the authentication phase. Where the contained parameters in a configure request packet are accepted by the peer, a configure ACK message will be returned. We can also consider the situation in which a configure request packet is sent for negotiation of parameters, which includes parameters that are recognized by the peer but not accepted. In such instances then, a configure NACK packet is returned to the sender to notify of this, and will typically contain parameters that may be used by the sender as part of a configure request packet that will allow a configure ACK packet to be generated. As a result of this, a new configure request packet will likely be sent, containing the modified parameters to the peer. Where a configure request packet is sent containing parameters that are not recognized or considered unacceptable by the peer, a configure reject packet will be generated by the peer and sent to the sender. In order to support this process, the configure reject packet will only contain those parameters that are not accepted. Once the configure reject packet is received, the sender is able to generate a new configure request but will have removed all of the parameters listed in the received configure reject packet. The configuration of PPP link encapsulation is configured in the same manner as other link layer encapsulation methods such as HDLC, and is done so on a per interface basis. From the example given here, we are able to see that the configuration of interface serial 1/0/0 on RTA is done so by firstly entering the interface view before changing the link layer protocol to PPP. Since PPP is the default link layer protocol applied in VRP, it is often not necessary to implement such changes. However, where required, a change warning will prompt the administrator to verify that the changes should be applied. PPP negotiation is likely to also define authentication parameters that determine the form of authentication that is to be negotiated as part of the negotiation phase of the PPP link establishment. Authentication is generally necessary to ensure that rogue devices are not physically inserted into the existing network. Without successful authentication, where authentication is applied, the peering devices are unable to establish the PPP connection. There are in fact two forms of PPP authentication that can be negotiated. We firstly take a look at the Password Authentication Protocol, or PAP as it's fondly known. PAP is basically an authentication protocol that operates based on a two-way handshake and will transmit passwords in plain text, which from a security point of view is not always the best choice for authenticating peers. We see as part of the example shown here the process that occurs during the authentication phase, where PAP has been negotiated as the authentication method of choice. Authentication is made up of an authenticator that is responsible for checking the username and password of the authenticated device, which in this case is RTB, against a local user table. The authenticator will send a response based on the result of the check that will either accept or reject the authentication request through the Authenticate ACK or Authenticate NACK packets. As an alternative to PAP authentication, PPP may be configured to support the Challenge Handshake Authentication Protocol, or CHAP for short, that operates somewhat differently from PAP and can be considered more secure, mainly due to the fact that the password used for authentication is not carried over the serial medium. Instead, CHAP relies on a challenge and response process that uses a value that is referred to as a secret, comprised of the secure password and other values such as the user ID that are used to generate a hash value. This is used as the response and returned to the authenticator that will verify the response by generating a second hash value and comparing both results. If the values match, the authenticator will notify the peer of its success or failure where the values are different. Once the authentication phase is complete, the network phase is initiated that relies on the Network Control Protocol, or NCP, to establish network layer protocols. Where IP is concerned, it is generally required that IP addressing be put in place that supports network layer communication. NCP uses the same packet exchange mechanism as LCP, and so will establish the IP addressing by sending a configure request that states the IP address that is desired to be used, to which the responding peer will generate a configure ACK to confirm the configured IP address is acceptable as the remote IP address. There are likely instances where it is expected that the peer provide the IP address information that is to be applied. The sender will generate a configure request that contains an address in which all 32 bits are set to 0. In doing so, it is basically requesting that the peer provide the IP address information. This is performed through the configure NACK message sent by the peer containing the proposed IP address to be used. A second configure request will then be generated by the sender containing the proposed address, for which a configure ACK will be sent in response. The implementation of PAP authentication firstly requires that the authenticator and authenticated devices be determined on the link. In this instance, we have set RTA to operate as the authenticator and RTB to be authenticated. As the authenticator, we are required to firstly set a username and password for the authenticated device using the local user command, as well as define that the PPP service type is configured for the local user RTB. It is also necessary that we specify that the interface is to support PAP authentication for PPP, and we do this again by using the PPP authentication mode command followed by the PAP parameter. For the peering authenticated device, which in this case is RTB, we must also configure PAP-based parameters in the form of the username and password that is to be sent to the authenticator using the PPP PAP local user command, where it is expected that the username and password match those set on the authenticator. Once PAP has been configured on both peers, we are able to use the debugging feature to observe the PAP operation. We show here the basic request and response operation that deems the peer request was generated as successful. The configuration of CHAP is very similar to that of PAP, in that an authenticator and authenticated device is firstly determined, followed by which the username and password to be used as the authentication parameters are set on the authenticator, by which the peering device will be authenticated. We again find that the local user command is configured to define the username and password to be used, and along with this the local user command that defines the service type to be set as PPP. For the configured PPP service type, the authentication mode of chat should be set. On the peer device to be authenticated, however, we find that two commands are used. The first of which to set the username for the chat authentication, and the second to define the password that will be used as part of the generated hash to provide the secret, meaning that this password will never actually be carried over the serial link. We have shown in both cases of PAP and CHAP performing authentication through the AAA architecture that will be looked at in more detail in later sections. However, it must also be understood that other mechanisms such as Radius or Huawei TACACS-based server authentication may be used to achieve similar results. Through the debugging feature, we can again follow the stages of authentication that are performed, in this case for chat. As opposed to sending the password as part of the request, we instead find that a challenge is generated to the authenticated device who provides a response in the form of a secret to the authenticator. The authenticator in this case determines that the received hash and the hash generated by the authenticator match, to which a success response is returned. So this brings us to the summary, and we just have two questions here. The first asks, following a configure request, what packet type is expected to be received before the PPP link layer can be considered established? Well, the peer will expect to receive a configure ACK packet in response to verify that the parameters are accepted by the peer for the PPP link establishment. Which protocol is used to perform the negotiation of IP addresses, and during which phase is this negotiated? It is the IPCP or Internet Protocol Control Protocol that is part of the NCP set of protocols which is used to perform the IP address negotiation, and this will take place during the network phase after any authentication is performed should authentication be configured.